Good afternoon, everyone. Thank you for joining us for the webinar, Lessons Learned from Green Stormwater Infrastructure from Green Design and Construction. My name is Elena Berg, and I am a planner with the Environment and Development Department of the North Central Texas Council of Governments, or NCTCOG. To give a brief overview of who we are, NCTCOG is a voluntary association of local governments. We are one of 24 COGs in Texas, and our main function is to transcend jurisdictional boundaries to promote sound development and facilitate cooperation among our member governments. As part of our water quality management planning work, we host workshops and/or webinars on water quality topics. If you have any ideas for future topics for these workshops or webinars, please feel free to send them to me. I'd appreciate hearing them. My email address is shown on the screen. We will have our main presenter, then we will have the Tarrant Regional Water District speak for 10 minutes to highlight their green infrastructure work in the North Central Texas region. Our main presentation today will be given by Jake Aalfs with the San Antonio River Authority. Thank you, Jake, very much for presenting today. Jake is passionate about promoting green stormwater infrastructure methods in order to protect the San Antonio River Watershed. He has a Master of Landscape Architecture and BS Electrical Engineering degrees from Cal Poly Pomona. Jake manages the Watershed Wise Rebate program. This program promotes the use of local programs from impact development design principles to treat stormwater. And now, Jake, I will transfer over to you. Thank you.
Thank you, Elena. And I'd like to thank the North Central Texas Council of Governments for inviting me to speak today. Here's an agenda of what we're going to cover. I want to start off by giving you a little bit of background upon myself. I have been managing the Watershed Wise Rebate program for the last 4.5, 5 years. And this program incentivizes green stormwater infrastructure in our community. We are really trying to get the word out on what low impact development and green stormwater infrastructure is, give lessons on how it can be designed, and also provide education to landscape architects, engineers, and contractors. Through this process, we have this learn by doing approach that we think is very successful, where we actually go out and design these, build them, and then evaluate them. We're involved from the beginning to the end, and also including operation and maintenance. So we're going to just have a quick introduction to low impact development and green stormwater infrastructure. I want to emphasize that in the time period that we have, I'm going to be skipping over a lot of details. Towards the end of this presentation, I will have a link to my email address and to our website, and also to a low impact development resources shared folder. We're also going to be briefly looking into some of the common treatment methods and really emphasizing the 4 methods that we use locally here for about 85 to 90% of the treatment. And then we're going to jump in and look at some of the lessons that we have learned along the way, and then show you some examples of the work. I work at the San Antonio River Authority, one of 24 river authorities in the state of Texas. We were formed by the state legislature, and our job is really to regulate the waters within the river, which means we primarily are concerned with water quality and quantity. We are the local FEMA delegate, and when it comes to water quality, we operate a laboratory that's fully accredited, so we can do testing and monitoring on our own. You can see our jurisdiction is the 4 counties shown on this map, and you can see also the watersheds that feed into the complete San Antonio River watershed. And this extends all the way from Bexar County, which right in the center there is where San Antonio is, all the way down to the confluence with the Guadalupe River right before it enters the Gulf of Mexico. And the reason why we're doing this is important. This is a map of our impaired segments, and you can see the central portion of San Antonio has a lot of impairments on our different segments. Most of these impairments are due to bacteria, and that is a very difficult constituent to treat. We are challenged by that, but we are working hard on removing some of these segments from that impaired list. So you're going to hear me mention the word stormwater runoff a lot, and I just want to make it clear what I'm talking about. This is runoff generated mostly from impervious surfaces. Those could be roofs or parking lots or roads, and then running off and generally entering into a stormwater inlet or pipe, as you can see here. And generally that water, by the time it gets into that pipe and into a creek, takes on this kind of brown look of chocolate milk. And a lot of times that is shown as the sediment that it's carrying. I want to emphasize that the more impervious cover that is in an area, the more stormwater runoff you'll have, and the more constituents are in that stormwater. This slide really emphasizes when we look at what a pre-development hydrology may look like, which would be on the left. That's an area that is mostly vegetation, trees, and grasses. And you can see how when it rains, a lot of the stormwater, or a lot of the water, rainwater, is actually infiltrated into the ground. You get a little bit of runoff and some evapotranspiration. And then conversely, when you compare that to an area that's highly developed with a lot more impervious cover, the amount of water infiltrating is greatly reduced and the runoff is greatly increased. And that runoff is what is containing this non-point source pollution like sediments, bacteria, metals, that is the main concern. Some more of the impacts are this increased volume of water causes erosion downstream. And these are real pictures along the San Antonio River downstream from San Antonio on areas that are just eroding and sloughing off into the river. We also have a huge impact of trash. The River Authority collects tons every year. And this isn't so much an issue other than as people causing it, but it is a large detriment to the river. And then we have pollutants such as metals, oils, and grease, often greatly attributed to the transportation systems of roads and highways, all of those entering into the river. And then sediment. Sediment is one of the largest problems here, and it comes from all sorts of different sources, from construction sites not having up protective fencing, to erosion, on and on. And then for us, bacteria. And really, bacteria is a very tricky constituent to treat in that wherever there's human activity or animal activity, you're going to have bacteria, and that bacteria can grow exponentially. So even though you may treat a little bit, it can still grow exponentially once it reaches a water source. And it is very difficult to treat. It is the cause for most of the impairment for the segments in our watershed. So I want to really cover, importantly, what is low-impact development. And when I talk about low-impact development, I'm talking about the overarching treatment of development. So it's basically not just the actual methods, but the overall method of designing things. So you're looking at the area holistically and saying, if I'm going to develop a greenfield site, I want to look at the slopes. I want to protect certain areas. I want to attempt to minimize the amount of impervious cover that I'm adding. All of these design principles are key to what low-impact development is. So low-impact development is not the actual method itself, it's this overall design philosophy. And it really wants to address stormwater quantity and quality, attempt to match the pre-development hydrology. So we want to make sure that the stormwater, amount of stormwater and quality of the stormwater that leaves a development is the same as pre-development as post-development. It also mimics natural processes such as evapotranspiration and infiltration. And one of the key concepts is treating the runoff as close to the source as possible, not letting it get into large volumes that are difficult to treat. And then all of those combine to having this on-site, small distributed practices to do the treatment. And overall, treating stormwater as a resource instead of just stormwater that needs to be put into a pipe and sent to the nearest creek. Then we look at green stormwater infrastructure, which are the actual methods to implement the treatment. And our manual, the city has adopted, has approximately 11 of these different methods. I'm showing 8 here, but in our experience, These four really account for about 85 to 95% of the treatment that we do locally. And so this is rainwater capture, permeable pavement, bioswales, and bioretention. Bioswales and bioretention are very similar to each other. The only difference being is that bioswales generally are more longitudinal, they're longer, and they have a slight slope, so they can convey water a little bit differently. You may also know bioswales or bioretention by the common term rain gardens. And there is a slight distinction between the two in that bioretention generally uses a specialized soil, and it oftentimes will have an underdrain. It's a more engineered and designed system. Getting into a little bit more detail on each of these, here's an example of rainwater capture using a cistern, capturing stormwater from a roof. And I want to point out, for our purposes, we do not allow any type of potable water backup for cisterns, meaning these cisterns cannot be filled with common tap water for any reason. One thing that we've noticed is oftentimes if they are filled with tap water, that they never drain down. So one of the main ideas is that when a rain event happens, these are empty. So we collect the storm water after a rain event and then slowly drain it off over a 48-hour period. Oftentimes when they have a potable water backup system, that system fails and they end up being full all the time. Here's an example of permeable pavement. And the key concept here is that that top layer of pavers has space between each paver that stormwater can seep through and enter the layers below. It often goes through a bedding layer, a sand filter layer, and enters a drainage layer of a lot of void space rock below, where it is held for a little while, and once it collects there, it can be carried off by the underdrain to a stormwater network. These systems provide a lot of holding capacity in that research shows that all the stormwater that enters through the top does not exit through the underdrain. So some stormwater is held in areas such as capillary action and treated in the biofilms that form in that area. Here's an example of bioretention. And in this example, we show a parking lot in the background where stormwater is entering through curb cuts, through an erosion control area, and to this lower basin that is covered with mulch and plants, and then infiltrates through a special bioretention soil mix, through a choker layer, and into a rock drainage layer below, where it can be collected and put into an underdrain, which can then daylight to another part of the site, or connect to a stormwater network. Oftentimes, bioretention areas may require liners, and those liners may cover the sides and bottom, depending on different characteristics. For example, if you have a bioretention area near a building or hardscape within 10 feet, you will want to definitely have lateral liners. And if you're in an area where the soil below it does not infiltrate well, you may want to line the bottom, or if you're over a recharge zone, you may want to line the bottom. Next example here is a bioswale, and this is a very distinct bioswale in a right-of-way, like right on the edge of a road, what some people would refer to as a parkway. So it's very confined bioswale. You can see the liner here on the sides. We show a PVC liner with geotextile on each side. It has the same layers as bioretention with a mulch layer on top, bioretention soil layer, a choker layer, and a drainage layer below with an underdrain. These are very adaptable systems, and this is in a very urban setting, but you can have bioswales in not so quite urban settings where they're so constricted. I also want to introduce the concept of a treatment train, and really what we're showing here is different treatment on your site. For example, the roof in this example is being treated by rainwater harvesting, and some of it is going to a disconnected downspout to a planted area. Stormwater that falls in our parking lot is being directed to a bioswale on one side and a rain garden on the other. So this concept of a treatment train is different treatment methods to treat the entirety of your site. What I want to emphasize from what we've learned going through this process for the last 5 years is that it really requires a framework. And what I mean by a framework is it's not just that we have a design manual, but we also have city code that specifies that that manual is to be used. The city code defines what low impact development is and the amount of treatment required to be called low impact development. We also have city and county codes that require inspection after construction of these features and also annual inspections of these features. So all these things together are what make a successful low impact development green stormwater infrastructure model work. With just having one or two is not enough. You really have to have complete buy-in from the definition and the code to requirements by the city. And I'll get into these in a little bit more detail. This is a picture of what our technical design manual looks like, and there's a link to it. It's published online as a PDF. And this really describes all the different methods of treatment. It starts off from the beginning on how to do site analysis. So the full low impact development design process of evaluating your site, looking for areas that you might want to protect, looking for areas that might infiltrate better based on soils. And then it goes through and asks you, as the designer, what constituents are you most concerned about? Are you looking to treat bacteria? If so, these are the methods that are recommended. And then you go on further to go through a design step-by-step for that method. So I would really encourage everyone to take a look at this manual. It is a very large manual, and it can be a little intimidating. Some of the portions of the appendix that you go through the design iteration process are some of the most informative portions of the manual. Here's some examples of what are in the manual. This is an iterative design process for bioretention. And it goes through step by step on how to size it, on different elements of the design that you may want to include. And there are also plans and sections in the manual as examples. Later on, I'm also going to give you a link to LID resources, and we have sample construction documents in there for each of the methods. The design manual also has specifications for materials. So what we're showing on the left here is the specification for bioretention soil. And this is important to have these specifications in your manual, maybe as a spec sheet, because these are what contractors are going to need to obtain and test to make sure that what they are building matches your specs. We also have details for connections of liners and different material suppliers locally for us that you can obtain them from. The River Authority itself does not recommend any contractor or material supplier, but we do supply lists of people that we work with without recommendations. And then most importantly, I refer to the Unified Development Code. And this is really the requirements for San Antonio that define what low impact development is. And this portion of the code, and there's a link to it below, specifies what the treatment quantity, the water quality volume is. It defines what it is and states here that it's based on the 90th percentile storm. And this is really looking at historic data for rainfall in San Antonio using an EPA method. And the 1.5-inch 24-hour storm is determined that 90% of the volume that falls in San Antonio happens in 1.5-inch design storms or less. So if I can treat a 1.5-inch storm, I am treating 90% of the volume that falls every year, which is a strong thing to do. Also, this goes through and shows that if you follow the standards in the manual, you are presumed to meet the following treatment levels: removal of 80% of the TSS and 60% of the bacterial load. And those are important because it's specifying the water quality volume as being treated and detained, but it's also specifying the water quality volume, what's being removed. There is an option in the code to use proprietary devices, and it goes on further to state that those devices must meet the volume detention requirements and these removal requirements for volume. Going through and doing evaluation of rebates, and the reason why we're doing rebates, I didn't mention earlier, but low impact development or green stormwater infrastructure is completely voluntary in San Antonio and Bexar County except for a very small area right next to the river in a couple of the Rio districts. In all other areas, it is completely voluntary, and so the River Authority is trying to incentivize the development of use of it, and we go through and provide these rebates, but we get a lot of applications. And one thing I have is a checklist of all the information that's necessary on the plan set for me to evaluate a design. And so I provide this as a good example, be able to compare design to design. And this includes things like contours, catchment areas, soil groups, and BMP drawings and sketches and sections, so that I am clear that the designer understands how they're calculating their treatment and what method they're using to do it. We also want to make sure that material submittals are carefully scrutinized. We go through and we have a requirement for the bioretention soil for them to submit at least a month ahead of time a test results for the soil itself. And then once the soil is delivered, we go in person and get a sample and have it tested. Too many times I have gone out and found soil that was delivered that I do not believe was the same soil that was initially submitted as with test results. And what happens a lot of times is you may get a soil that doesn't meet the specifications, and it is difficult in some cases to meet the specifications for phosphorus, and you end up having a bioretention area that as water flows through it is really leaching phosphorus instead of capturing it and holding it. So it's actually doing more harm than good. We also have construction inspection checklists, and this is as a BMP, a best management practice, or a method is being constructed, we go out and make sure we inspect at certain times, and these are the things we're looking for. We want to see under drains, we want to see materials, we want to look if materials are completely washed. We want to make sure that they have their stormwater protection up during construction and that they're building it correctly, not compacting the soil while they're building it, so on and so forth. So it's very important to have these inspection checklists. And we also have learned that operation and maintenance is a very important part of low impact development, green stormwater infrastructure. These methods, once they're completed and enter the cycle of being used, cannot be maintained by just a normal group with weed whackers and a blower. Oftentimes, it takes a little bit of special knowledge, and we do provide training to maintenance staff. As part of the manual, we have checklists for each of the methods on how often, and we have recommendations of how often to go and check that method, and specific things to look for. For example, on this maintenance checklist for bioretention, you can see there's monthly recommended checking of each of these, and if you see standing water, what you can do to address it, and what you expect the results to be after the maintenance is performed. Now I'm going to get into some of the specific examples from projects that are either rebate projects or projects that were built next to the river and we had a private contract with the developer to do stormwater treatment. None of these pictures, I don't believe, are from school grants, but we also have a school grant program where we do smaller projects at schools. So this is an example of a multifamily apartment complex right on the edge of the San Antonio River. And this is during construction. They built a bioretention area towards the end of a street that is right next to the river. And what they did was they went through and built the bioretention area, but they did not protect it during construction. And you can see the sediment has entered through the curb cuts, covered the whole top surface, and basically plugged it. Water will no longer flow in there and infiltrate down through the soil layers as it's supposed to. So this would have to be scraped off and dug down a little bit, and new mulch, possibly new soil, would have to be brought in. And then we'd have to go ahead and verify that it is infiltrating at the proper rate. So it could have been easily addressed just by putting sandbags at the beginning of these curb cuts, or by covering the whole area with a geotextile until the rest of the construction was complete. Another important thing to look for are spot elevations in your design plans. It's very easy for people to assume that gutters are going to flow correctly, but we see examples here where we have a curb cut and the stormwater is entering this picture from behind me, and it's intended to flow down here, enter the curb cut, and into the bioretention area. But this portion of the curb cut I often like to see sloped down and then have a 2-inch drop before it hits the erosion stones. But in this case, the actual flow line continues along the gutter and goes straight into a drain. So most of the stormwater in this case bypasses the curb cut completely. I also want to point out in this bioretention area, I would like to see a larger drop off here with more room for ponding. So after you see that example, you can see definitely in the example on the right that stormwater flowing down this gutter line will never enter that curb cut. There's a small lip along this edge, just completely not constructed right. And what we've kind of learned is that curb cuts, things like this are new, and contractors don't really understand that that small detail is so important. When it comes to these features though, the small details are very important. When the water does not enter the BMP correctly or the feature correctly, it never gets treated. Other small details related to drains also can be affected here, and I'll show an example of that coming up. So here's an example, and you can see in the plan there is a ponding area, the basin for a bioretention area, and they call out a 6 to 9 inch ponding depth. That area is basically up to the bottom of the invert of this drain. When it's constructed, what we often see is that that ponding area is neglected by either being filled in, the basin's not dug out enough, or the drain is not elevated. It's cut off at ground level like normal drains are. So this is just one of the things we always look for, is to make sure that the basin is built correctly and the overflow drains are at the correct elevation. That volume that is stored above the overflow is volume that eventually infiltrates in it and is treated. So it's part of the calculated treatment volume. And without it, you're not getting the amount of treatment that is specified. Another good example that we see is lacking a little bit is coordination. And generally, this is coordination between the landscape architect and the engineer. Oftentimes, the landscape architect's plans do not incorporate drainage portions from the civil engineer's plans, and vice versa. The civil engineer's plans don't include landscape amenities. In this example, this is another apartment building right next to the river, and when we reviewed the plans, on the landscape plan, we saw a dog park, but we did not see a drainage system in the middle of the dog park. And on the civil plans, we saw the drain, but we did not see a dog park around it. So when it was reviewed, it was not caught until they actually built it. And right in the middle of the dog park is a drain inlet that drains right to the river. We have since then gone back in and required the builder to install an inline filter to handle this. But coordination is the main reason why this happened, or lack of coordination. Also, excavation is an important point to look at. It's very easy on these design drawings to draw a vertical wall to be excavated and filled back in with drainage layers and soil layers. In real life, it's a little bit more difficult to construct and to dig that vertical wall. We oftentimes will recommend that maybe they lay back the excavation a little bit at a slope because it's easier to dig that way, and then build it back maybe with a vertical wall. At least what I always recommend is to have all the materials on site before you start digging, so that as soon as you dig the trench to the proper depth, you can start building back the layers the same day. In examples where this didn't happen, the contractor digs one day, may decide that he's not going to work on the trench for another week, and inevitably it rains during that time. And it's not just a regular 1-inch rain, it's a 5-inch rain, and the whole walls collapse in, and they end up having to go back and dig it back out. And this happened on this project. It's also very important, if you are planning to do infiltration into the in-situ soils that are there already, that you perform a geotechnical evaluation of the area with borings and infiltration rates. The one failure for bioretention is not draining correctly. In areas where you have good infiltration rates, it is not required to have an underdrain, but you do need to verify that and have a safety factor. And we always have the boring to at least the bottom depth of the design. Another part that we've really had a lot of benefit with is summarizing project benefits, so that when people ask what was the good that came of this project, we can point to them. Some of the important things we look at are what the target volume for the method was and how much they actually treated, and then we can show the percent of volume captured, and from that we can estimate the annual volume of bacteria removed in colonies per year or sediment removed in pounds per year. So in this example, we see the target was about 1,250 cubic feet. They actually provided treatment for quite a bit more, and from that we could calculate their annual volume captured is almost 100% for that specific catchment and treatment, resulting in these further benefits. We put a heavy emphasis on training and education. We have partnered with the county and the city to have a credential program that provides credentials for people to perform construction inspections or annual inspection and maintenance inspections that do not have another type of degree, such as a landscape architecture license or a civil engineering license. We provide that training and register, certify people, and keep track of that and make sure that people come back every 2 years to recertify that. We also have a comprehensive design class where we go through site planning and design and cover as many of the methods as possible. We also can tailor training. For example, we'll help the city on training maintenance staff, and we can conduct tours as needed. Now we'll jump into some of the real-world examples. And this is a permeable pavement installation in Leon Valley. One of the important things I want to point out about permeable pavement is that it treats the water that falls on it and an equal area that can flow to it, but it's limited to basically that treatment area. You don't want to have a large catchment area flowing to the permeable area because that tends to clog them. So in this example, half of this parking lot, which is regular asphalt, flows on to the permeable area, and the other half flows over here. Here's a close-up on the left during construction as they're digging down and getting to the proper depth and filling back up with the gravel and under drains. And then on the right, you can see the finished product. Another example, and we saw this a little bit earlier in some of the examples where we looked at the trenching. This is the City of San Antonio Development Services Department parking lot. The Development Services building is located right here. Right across the street is a relatively new parking lot. And this whole parking lot, about 95% of the runoff from it is directed to a bioswale. This bioswale is about 250 feet in length, and the complete width is about 16 feet. The bioswale portion is right in the middle, about 8 feet wide. And it is a bioswale in that this end and this end are higher and flow towards the center, and there's an underdrain that connects about right here to an inlet on the street to carry away the treated stormwater. Here's a picture right after construction was complete, December 2016. You can see all the plants are relatively small. I also want to point out it does have temporary irrigation. Since then, that irrigation has been turned off. And then compare that to the picture on the right just a year later, how the plants have grown, and since then have even grown more. Some of the nice parts of this project are that it uses rock mulch. The maintenance is fairly low on this. We do get some weeds through there, and some actually of the native plants that are planted there are spreading out and growing in unintended places, so there is a little bit of maintenance on trimming those back. But all in all, a very successful project. Another one is the expansion parking lot at the museum, which is our local children's museum. And this was built as kind of an expansion after the museum was so popular they needed another area to have parking. So this one area was added, and it basically treats all the stormwater that falls in the parking areas in 2 bioretention areas. These are square basins, and good example, as you can see, the curb cuts up here where the stormwater flows down, a good erosion control on the slope and as the water enters the basin, and a nice high ponding depth. You can see the control on that is about 12 inches all around. The water then spreads out over that whole area and infiltrates down. And successfully, you can see it's planted with horsetail, and just a year later, how much that growth has gone through. This may get some irrigation, but most of that is from stormwater. Another good example is this project, which is an urban infill called Urban at Olive, where an empty vacant lot was purchased by a developer, and they built in some smaller single-family houses. And you can see there's an internal alley here, and then another alley back here, and a little walkway along here. The way the slopes work on this project is most of the stormwater is along this high port falling on these roofs, and in this alley, flow to this central park area, and then down a bioswale through the development. So in this picture, you can see the alley up above and how the stormwater flows through and enters the bioswale. This is just the beginning. It turns around a corner and flows down the street. Now remember, this bioswale is infiltrating the water as it flows through it, so you probably will not see a lot of surface flow except in very large events. And here's a picture from the street. That stormwater was up here and continues down the street here. It does have an underdrain, and that underdrain daylights down the street a little bit down the way. Real interesting story about this project is that the developer ended up building this row of houses first, then they finished the bioswale, and started construction on this last row. And that last row sold out so quickly, and most of the people, they attribute it to the beauty of the bioswale and seeing how this area looked as they were walking through. And we heard that from the developer, so we're very pleased to hear that. Here's another example. This is MP Studio, and this is an example of a treatment train showing how they're doing multiple treatments. And this treatment train is from one treatment to another, basically going from cistern to bioswale. MP Studio is a local landscape architecture firm, and they have retrofitted a Quonset hut. On both sides, they have a gutter where they collect all the roof runoff into a cistern. There's one on this side and one on the other side. This cistern then slowly drains, as I mentioned before, over 48 hours, to a bioswale located right down here that looks like this. And that bioswale flows out and around the corner where it daylights on the street. That bioswale also collects all the runoff from this parking lot. And it's a good example. During construction, you can see the liner on the sides because you don't want to be infiltrating stormwater right next to a parking lot. This liner keeps that stormwater controlled. You can see the underdrain with a clean out, and that goes all the way around the corner. And also a good example of, this is not a planted bioswale at all. From the surface, they wanted it to have a modern look, and they used just a basalt rock. You really can't even tell how it functions unless you knew. And I think maybe our final example is Confluence Park, which is a new park here in San Antonio near the confluence of the San Antonio River and San Pedro Creek. Many partners take part in developing this, and really want to show also the treatment train here. All of the stormwater that falls on impervious surfaces in this project stay on site and are treated. There is permeable pavement in the parking lot in the shape of these basalt rock parking areas with drainage below, and all the stormwater that falls on pedals such like this are collected in drains, and all of that runoff is directed to a central water catchment system which is located underground. You can see it on the picture on the left. It is constructed using the crate type system, which is wrapped in geotextile, which creates a large void space, which is then covered with regular soil, bioretention soil, and planted with native grasses. So this area can hold water underneath and has a large basin on top. They do use some of this water to irrigate the whole park. And a very good example, I recommend a visit there next time you're in San Antonio. That pretty much concludes my presentation. I know I've gone through a lot of information, and I want to provide a couple links. This is a link to a website where it goes through our rebate. I did not talk about a lot of the process for the rebate, but this website goes through and provides the whole process, how applications are submitted, how we evaluate them, scoring rubrics, different checklists, and different requirements during the rebate process. I also included a link here to a shared folder that includes all sorts of different low-impact development resources, ranging from plant lists to example construction documents, to material suppliers, to contractors that we've worked with, a whole list of resources. And I want to go ahead and provide some information, my contact information, and open everything up for questions.
Thank you, Jake. The first question I see is, I've seen this US EPA diagram before. I think that's referring to the one about the increase in runoff in an urban setting, Jake. And the question is, curious if we have cross-check with local solids for North Texas, or if we see a similar breakdown.
I'm not exactly sure how to answer that question for North Texas, but I would think that in general, those amounts could be carried over to any urban developed area.
Another question we have is, do you or how do you track public and private GSI projects?
That's a good question. We do accept applications from both public and private developers or governments. And so far, we've had a fairly even mix. We have had quite a few public ones early on, and those oftentimes will be like parking lots or right-of-ways. We basically track all of that internally. We do not differentiate between them in that one gets any kind of priority over another, nor do we say that one is better than the other. We're really looking right now when we look at rebates, we have a scoring rubric, and that is published on our website. We're really looking at a list of 6 things, really coming down to where is the project located? Is it in a high priority watershed that we have determined by modeling? How much stormwater treatment is it doing? And how close is it to a receiving water body? You can look at the whole rubric on our website, but those are some of the 3 of the main points we look at when deciding between a project. But I would say that the public projects are successful along with the private ones. We want, I think, eventually to have more private applications for the rebate. And I didn't mention it, but we also are partnering with the local city, county government on doing some bond work where we will pay half of the increased cost to do green stormwater infrastructure. And so maybe some of the public projects will be going more of that shared cost with the city government.
Who performs annual inspection? Is it in-house staff, and how many staff?
Well, that's a good question. The annual inspection is actually a requirement of both the county and the city, and we provide a certification program so that anyone can become certified, become one of those inspectors. They can also be inspected by registered landscape architects or civil engineers with a license. We have our own staff in-house that does some monitoring of the rebate projects because we have a rebate agreement with the recipient of the rebates to keep these operational for 3 years. So our team goes out and evaluates the functionality in regard to the rebate to make sure that they're functioning and so that our money is well spent. But the city and county have their own requirements. So everyone that does this in the county or city has to have that annual inspection.
The next question is there a particular reason why those 4 LID methods are used more than the others?
I would say there definitely is a reason, and it comes down to value, meaning the cost, the treatment cost per, let's say, cubic foot of stormwater. Your best value is bioretention or bioswales, in being that the cost of construction is less than the other methods. Permeable pavement and cisterns are more expensive, but they allow you to treat areas that you may not have an opportunity to treat for lack of space or location to do bioretention. So for example, if you have a large roof area but you don't have a planted area where you could do bioretention, a cistern makes a lot of sense. Or if you have a parking lot that you just do not have any planted areas next to, at least you can get some permeable pavement in there to do some treatment. The reason we go with these 4 is they're the best value and they work well together. The other 7 or so methods are things such as a wetland or an extended detention basin, which in some cases are for larger areas, or a wetland requires an area that always has water. So they have other requirements that aren't as common. One of the other treatment methods also is sand filters. And sand filters are common around Texas. It's not one of the preferred methods in that it may not always look that great, but it is a method that can be used.
And the next question is, for proprietary structures, do you use TAPE, TAPE/TARP for access removal specifications?
We do not use the results of the tape testing for the TSS removal, but we do look at, so this is in the code, the city code, really, and basically it says you can use any proprietary method that you can prove removes that 80% of sediment and 60% of bacteria. The tape testing protocols do show that in many cases. We also defer a little bit to TCEQ in that they have some approved proprietary devices. And the reason I bring that up is that there are proprietary devices that meet tape requirements, but that TCEQ has not approved. So there's a little bit of a wiggle room there.
There are many questions, Jake. We're going to take one more for you, and then we'll turn it over to the Tarrant Regional Water District. The question is, you mentioned you collect information about the gallons of water each project treats. Do you know the total number of gallons treated?
I have it in a spreadsheet, and then basically I could answer that question in an annual treatment in cubic feet. I mean, I could convert it to gallons. I don't have that on the tip of my tongue right now, though, but if someone shot me an email, I do have it in a spreadsheet.
Right now, we will turn it over to Tarrant Regional Water District.
Hi everyone, my name is Michelle Wood Ramirez. I'm a watershed coordinator with Tarrant Regional Water District.
And my name is Brenton Dunn. I also work for Tarrant Regional Water District in the Environmental Department. And Tarrant Regional Water District is a water supply, flood control, and recreation. Those are the 3 aspects of our mission statement here in Fort Worth. And stormwater has a piece in each one of those mission statements. We're going to focus on our interaction with stormwater and our program for that today.
So because our mission statement includes water supply, flood control, and recreation, we decided as a district to improve our campus for stormwater and aesthetics. So a few years ago, we started some demonstration landscaping that promoted best management practices for commercial and residential users that we could showcase and do tours through. And that's kind of grown into a campus-wide movement that has garnered a lot of support from staff and executive staff as well, because it has improved the walkability and made the campus a lot more interesting and beautiful. So it's changed, and we've call it now the TRWD Rainscapes. So some of the examples that we have showcased here on our campus are rainwater harvesting, the bioretention, dry detention ponds, and the dry rock creeks where the stormwater meanders after a rainfall event. We also have a rain garden called the Overlook, and our newest, most exciting piece that we've built is the wetland, the redesigned stormwater wetland down at the bottom of the property, and we're able to collect all of the stormwater that falls on the campus and treat it. So we have our own treatment train through the watershed on the campus, and we have a fully functioning stormwater wetland. It's the region's first stormwater wetland that's been redesigned. So it was an existing detention pond, retention basin, but it has been redesigned with the city and re-permitted. So we're really, really excited about how the increase in wildlife, the increase of diversity we've seen, and just it was installed in April. So we're really excited about how well that's performing. In addition to the demonstration landscaping that we have, the TRWD Rainscapes on campus, we're also going to be focusing on the education and outreach side of it as well. And this is an example of an Esri story map that we've put together for the very first piece that we built, which is the overlook I mentioned earlier. So this is a series of pictures and information about native landscaping, water conservation, and different green stormwater infrastructure that we've included here. So we can see that we have different kinds of plants, and we also have different kinds of impervious pavement, and a little section for people to sit and enjoy the landscape. So this is an example of what we have. We'll provide links for this at the end, and if you have any questions, just let me know.
And in parallel with what Michelle was speaking about, we have developed a regulatory program along the Trinity River with the development and the redevelopment happening on both sides. We have instituted a requirement for stormwater quality in coalition with the city of Fort Worth, and they follow the ISWIM program. However, the stormwater quality is optional. And so we've made the stormwater quality through our program a requirement. We have used local rainfall data with an urban landscape, and we have put together a formula that provides for the designer to come up with a water quality capture, and then he's required to treat that quantity of water. Once he is treating that, then he will have been able to meet our quality requirement. We provide a variety of BMPs to choose from. The designer can pick those according to the site and what best works for that development. We review and comment on those plans, and then once we reach a final acceptance of the BMPs that will meet our requirements, we provide a letter of an acceptance along with the City of Fort Worth Stormwater Facility Maintenance Agreement, because we are co-permittees with the City of Fort Worth. That's a very quick rundown of our requirements, and I would love to visit with you more, but that's a wrap. So I'll turn it back over to Michelle.
So hopefully we have been able to really quickly touch on the higher level, the overview, why TRWD is doing stormwater, why we care about stormwater, why we care about protecting the Trinity and the water quality and quantity. But also we want to be able to connect with a broad and diverse group of people. So again, the TRWD Rainscapes is how we are able to connect those requirements and those examples of green stormwater infrastructure, low impact development, all of the buzzwords, but also we want to be able to teach them to landscape architects or planners or engineers. So getting the examples out and tours out on our campus will help us talk about stormwater, get the awareness out, and also have a healthier watershed and a healthier Trinity River. So we're really excited about the TRWD Rainscapes on our campus and our stormwater initiatives. So if you have any questions, feel free to contact Brenton or I. We have a brand new website, trwd.com, and you'll be able to search for the water quality guidance manual as well as a story map that we have of the rainscapes. We've attached those links too, so feel free to reach out to us or dig through the website or follow the links that we've provided so you can learn more about the stormwater efforts on our campus.
And this webinar is now over.